Okay, so in this lesson, what I want to talk about is this idea of what's called background radiation. So right now, as you sit here listening to this video, there's a lot of background radiation that is all around you, and really the idea of the lesson today is to really kind of look at what are some of the sources of this radiation and where does it come from? Because it is all around us, it is present, it's a naturally occurring phenomena that happens. So if we think about the background radiation, a lot of that, so if we have a look here at this table, this tells us that 60% of the background radiation comes from this substance that is known as radon gas. So radon gas is an element that is radioactive. So if we have a look on the periodic table, so here we have a periodic table of elements, and we'll notice that this group here, these are known as the noble gases. So they're the noble gases. And if we look down here, so this is our radon here. So this is elemental radon. So we have elemental radon here. So this is where it shows up in the periodic table. So something to kind of think about is, number one, it's a gas. Okay, it's a noble gas, but it exists in it as a gas. And number two, this gas, so these particles of radon, or sorry, these atoms of radon, okay, are radioactive. So they actually give off radiation. So that means that the nuclei of the radon atoms are unstable, and as a result, because they're unstable, they just generate radiation automatically. So if we think about the types of radiation, so radon gas is what's known, it's an alpha particle emitter. So what it does is it gives off these alpha particles, and alpha particles by themselves are not they basically don't travel too far, as in like a piece of paper, for example. They're not very penetrative. So a piece of paper, even a few centimeters of air, will actually stop these alpha particles traveling. But the problem with the alpha particles is that they're ionizing. So if you were to breathe in alpha particles, for example, it can cause molecules within your lungs, within the cells within your lungs, to become ionized, and that can cause serious problems. Now, the fact that radon is a gas. So imagine this is our cloud of radon. So it's a gas, and like we can easily breathe in that gas. But not only is it a gas, but it's also giving off radiation. So it's constantly just emitting these alpha particles. So those two properties together create a problem for us in relation to the background radiation. So if we have a look here, so this is just a diagram basically that shows all around the country of Ireland, for example, like where the levels of argon are fairly high. So we can see here where it's this kind of red color. So up around here, for example, and here, the percentage of argon is pretty high, and then we have places like here, the percentage of argon is pretty low as well. So what has actually happened is when new houses are being built, they have to put in what's known as a radon barrier. And basically what that will do is, so imagine you have the foundation of the houses here, and they'll put this radon barrier across it like so. And this is your ground. So imagine then there might be like a cave underneath the ground, for example, and that's full of radon gas. And that radon gas can seep up through the concrete, and it can actually get into the building and accumulate in the building. But if there's a barrier here, like so, that will stop the radon gas getting up, and it'll stop it accumulating within inside the building. So this here kind of shows. So you can see here, and this just shows different types. So for example, high radon potential. So that's kind of areas like where there's, where there's fault lines and where there's caves like that. So what can happen is the radon can build up here in high concentrations, and then what it can do is it can actually seep up up into buildings, for example, if there's no radon barrier there. The same when you have like natural fault lines. Again, this radon can it's a gas, so it's going to rise up and you have a high buildup here. Now, if you take other places, so for example, granite and where there's coarse soil, there's a low radon potential here, because if you think about the gas, it's not easy for the gas to travel through this material as well. And then the same as well, like where you have limestone and you have glacial deposits here, for example, again, it's just hard for this radon gas to travel up into buildings. Now, where it builds up in buildings, that's a major problem, because it's a gas, but it's emitting these alpha particles. So if you're inhaling radon gas constantly all the time, you're constantly inhaling this radioactive substance into your lungs. And if this radioactive substance in his lungs, these alpha particles that are being generated can cause ionization in your lungs, and it can cause health problems down the line. So that's one. So then if we think of rocks and soil, so there's all different types of materials that rocks and soils are made of. They can contain uranium and different, trace elements that have isotopes that are radioactive, and as a result of that, these contribute to the background radiation. So the overall radiation, let's say, that's in your background. Food and drinks, then also as well, and this is kind of an unusual one as well. So if we think about, so for example, potassium. So if you take the element potassium, so this is potassium on the periodic table. So there are isotopes of potassium that are radioactive, and as a result of that, they give off radiation. And some of the isotopes, for example, of potassium, they just spontaneously break down, and their nuclei are unstable. And in the case of, so if we have a look here, so some of the isotopes of potassium, for example, they have a really, really long shelf life, or really long half-life, should I say. So if we take this, for example, so this here is the half-life of one of the radioactive isotopes of potassium. So it takes this long for let's say, the concentration of the radioactive isotope to reduce by half through giving off radiation. And the type of radiation the potassium isotopes can give off, they give off both this beta, they give off beta particles, and they also give off some gamma rays as well. Now these are a lot more penetrating than alpha particles, but again, the amount of background radiation that's given off, or the amount of radiation that's given off by, for example, the isotopes of potassium that are in things like bananas and also Brazilian nuts as well, it's very, very low, in that it doesn't generally cause any major health concerns, because the level of radiation is quite low. Even though it's quite penetrating, the levels of it are very, very low. But if we have a look here, so there's all different. So if you think about, plants, then they will take up nutrients from the soil, and some of those nutrients will be elements that have isotopes that are radioactive. And the same as well with drinking water, for example. There's going to be potassium and things like that that will naturally get into the water, and as a result of that, food and drink are by their nature are going to have radioactive isotopes present in it as well. So again, this would contribute to roughly, if you're to overall the background radiation, to be about 10%. We have then cosmic rays. So again, we have all types of radiation that's coming from outside from out in the cosmos, and again, they bombard the Earth all the time, and that contributes to roughly about 10%. We have then, let's say, medical sources. So if we take, for example, we have the radioisotope, which is known as cobalt. So this here, so cobalt is an element, and there's an isotope of cobalt called cobalt 60. cobalt 60. So it's just an isotope of cobalt, and it's very, very radioactive, and it gives off these gamma rays. So if you think about, and that cobalt 60 is used, for example, in cancer treatments and to kill and treat tumors. So they use the high penetrating abilities of the gamma rays that are emitted by the cobalt 60 to break up and kill cancerous cells and tumors. And again, like what's happening is, you know, some of these isotopes have very, very long half-lives, so they continue emitting radiation over a long period of time, and that also contributes to some of the background radiation as well. But again, it's still very, very low. Then we have like fallout from weapons, so you have nuclear waste, and then you also have fallouts from weapons testing as well. So if we think about, for example, when the US and Russia were carrying out nuclear testing, so they discovered how to split the atom, and they used uranium, which again is an element that's here, for example, on the periodic table. So uranium, so this is it here. And again, uranium, you know, a very small amount of uranium, when the nuclei of those atoms are split up, they give off huge amounts of energy, which can be weaponized and used to fight in wars, which we've seen. You know, 2 Japanese cities were leveled to the ground during the World War, and that was again using nuclear weapons and radioactive isotopes and radioactive materials such as uranium. And then also as well, we have, like, you know, we have, for example, in the US and in the UK and also in Russia as well, they are able to use nuclear materials such as uranium to power stations and generate electricity for their peoples. And again, sometimes that can go wrong, and we have the case in Chernobyl, for example, where a nuclear power plant basically had a meltdown, and as a result of that, a lot of that radioactive isotopes that were generated were spread all across Europe and put up into the atmosphere. And again, they have very long shelf life, or half-lives, should I say, and as a result of that, they would be also to this day still contributing to some of the background radiation that is present all the time. So that's what we mean by background radiation. So again, as you sit here right now, you are going to have alpha particles, beta particles, and gamma rays passing through the environment that you're actually in right now. These become major problems when they're highly concentrated. So when you have a huge high concentration of gamma rays, so for example, if you like in a nuclear reactor, you're going to have a lot of radioactive material that's highly concentrated. So you're going to have lots of gamma rays, for example, or beta particles being generated and fired out all the time. And obviously, if you know, the more of these, the higher concentration in the same area of these radioactive isotopes, it generates, for example, it spits out particles and rays that can be damaging to human health. But again, in small doses and small concentrations, they're not a major concern for health, going by what medical experts say. So that's what we mean. So that's what, when we talk about background radiation and some of the sources of background radiation, that's what we're talking about. Okay, so thank you for listening.